Back, everyone. And this week we're going to be talking about the atmosphere, weather, and climate. So we're making kind of a shift from our focus on the geosphere and the hydrosphere in some of our recent lessons into talking about the atmosphere as kind of the center of our concern for the rest of our semester. But we'll see that all these different parts of the Earth continue to interact. We can never talk about just the atmosphere in isolation from all the other parts that make up the Earth. So, our lesson goals here are first for you to be able to describe the structure and composition of the atmosphere, then to be able to identify the difference between weather and climate, and finally to be able to explain the causes of different climates in different places. So why is the climate in one part of the world different from other parts of the world? So let's start by taking a look at our atmosphere. So the atmosphere is this thin envelope of gases that surround the Earth. So in comparison to the diameter of the whole Earth, the atmosphere is very, very tiny. So it occupies only a tiny fraction of the diameter of the entire Earth. But it's of course very important for us because we all live in the atmosphere. Right? You are surrounded by the atmosphere on all sides right now, except for the bottom of your feet or the bottom of your butt as you're sitting in a chair. So the atmosphere is very important to us, and the atmosphere is divided into different layers that behave in different ways. So just like the interior of the Earth was divided into those different layers, right? We talked about the crust, the lithosphere, the asthenosphere, the mantle, the core. We can also distinguish different layers of the atmosphere. So at the lowest level of the atmosphere, we have what's called the troposphere. And this is the layer of the atmosphere that nearly all humans ever have spent our entire lives in. So the troposphere goes up to about 10 kilometers in height above the Earth's surface. And so that is high enough that encompasses even the tallest mountains on the planet. So you go up to the top of Mount Everest, you're still in the troposphere. Commercial jets, if you've taken a long distance flight, that's still flying near the top of the troposphere. So this is a very important layer of the atmosphere for us. It's also the densest layer of the atmosphere. So the atmosphere is held onto the Earth by gravity, which leads to the lower levels of the atmosphere being denser, more air packed in there, and it gets less and less dense as we go up. But even within the troposphere, we can see those differences in the density of the atmosphere. So if you were to go up to the top of some of these very tall mountains, then you would be able to actually experience the air being thinner up there. It would be harder for you to breathe because there's less air. A few years ago, I helped lead a group of SRU students on a trip to China, and one of the things we did while we were there was that we went up to the top of Jade Dragon Snow Mountain, which is in the Himalayas. So it's not quite as tall as Mount Everest, but it is quite high above sea level, and we all had to take little personal oxygen tanks with us because the air was so thin up there, it got hard to breathe, and you got tired really easily, and you had to stop and puff from that oxygen tank while you were up there. So, humans can't really survive outside of the troposphere because the air is going to get too thin for us. But there is atmosphere up there above the troposphere, so as you continue going up in the atmosphere, you get to a layer called the stratosphere, which you can see runs from about 10 kilometers up to about 50 kilometers in altitude. And so in the stratosphere, we get things like some of our highest clouds that we can see. Weather balloons go up that high in order to get a full picture of the portions of the atmosphere that are most important to affecting us down here on Earth. And one very important thing that exists in the stratosphere is the ozone layer. So the ozone layer is a portion of the stratosphere that has high concentrations of ozone, which is a molecule comprised of 3 oxygen atoms connected together. So normal oxygen, the oxygen that you're breathing in right now is O2. It's two oxygen atoms connected together into a molecule. Ozone has three oxygens. And ozone has a very important property of blocking ultraviolet radiation from the sun. So the ozone layer is pretty important to us because otherwise we'd be getting fried by that ultraviolet radiation and getting skin cancer much more easily. And unfortunately, because we only have a semester here, we can't spend a bunch of time talking about the ozone layer and the dangers to the ozone layer from human activity. But luckily, the chemicals that people created that were destroying the ozone layer in the late 20th century have now been largely phased out. And so the ozone layer is repairing itself. And so it's a great example of one of these environmental problems that we've actually made really good progress on. So the thinning of the ozone layer is no longer such a big threat to us as it was in the past. Even when I was your age and I was in college, we were still very worried about the thinning of the ozone layer, but that has really turned around. So the ozone layer is great. It's important. We were causing some problems for it, creating chemicals that were destroying it for a while, but it is on the rebound. So that's the stratosphere. If we were to continue going up above the stratosphere, we would get to the mesosphere. And so in the mesosphere, we get other atmospheric phenomena, like a lot of meteors are visible coming through the mesosphere, where the air that's up there is causing friction with that meteor, causing it to light up so that you can see it in the sky. And then above that, we get to the thermosphere, the outermost layer of the atmosphere. And so there is no clear boundary on the outside of the atmosphere. In the same way that the outside of the lithosphere, it's very clear where the ground ends and the next thing, the air, begins. With the atmosphere, because it gets less and less dense as you go up more and more, it just kind of gradually fades out. So as we get into the thermosphere is getting just less and less and less dense as you go out until we are effectively in outer space. But there's not a neat boundary that separates the atmosphere on one side from space on the other side. So we have these different layers to our atmosphere. We're mostly going to be talking about what goes on in the troposphere because that's where we live. That is the layer that has the most effect on people. So we've got all these different layers of air, so we can look at what air is actually made out of, because air is a combination of different molecules. It's not one thing. So what you see here is a diagram of the typical composition of dry air in the troposphere. So the air that you are breathing in and out right now should more or less correspond with this pie chart here. If it doesn't, if you've got a lot of something else that's not showing on the pie chart, then you may be in trouble. So what we can see is that over 3/4 of our air, so 78%, is made up of nitrogen. So that's N2, two nitrogen atoms connected together into a molecule. That makes up over 3/4 of the air that you are breathing right now. And then nearly all of the remainder, about 21%, is oxygen. So this is regular oxygen, O2, two oxygen atoms connected together into a molecule. And then nearly 1% is argon. So that is a gas that doesn't form molecules, it's just individual argon atoms. So between the three of those, that adds up to very close to 100%, nitrogen, oxygen, and argon. So that means that other things in our atmosphere, percentage-wise, are a very, very tiny fraction of that air. So you see some of the major ones listed there: xenon, neon, hydrogen, helium, krypton, and carbon dioxide. So carbon dioxide makes up well under 1% of our atmosphere, just a tiny little bit. So on the one hand, you may think, well, then why is carbon dioxide so important? But even that tiny bit of carbon dioxide has major effects on how our Earth system works. And because carbon dioxide is such a tiny fraction of our atmosphere, that means that human activity is very easily able to increase that carbon dioxide by a significant percent. We can very easily double the amount of carbon dioxide in the atmosphere when there was only a tiny bit there in terms of percentage of the total amount of gases there. On the other hand, to make a really substantial difference in the amount of oxygen in the atmosphere would be much more difficult because there's just so much more oxygen to start with. But because carbon dioxide was a small fraction to start with, then adding carbon to the atmosphere can change that percentage very significantly, much more easily. So these are the main constituents of dry air. And I'm saying dry air because you'll notice that one thing that's not on this list is water vapor. So this is air that has had all the water vapor taken out of it because the proportions of these other gases are relatively stable. So the ratio between nitrogen and oxygen in our atmosphere is pretty much always going to be the same, whereas the amount of water vapor in the air can vary drastically. You can have lots of water vapor or very little water vapor, and that can change very quickly. It can change from one place to a very nearby place by quite a bit. So there's so much variability in the amount of water vapor in the air that it would kind of mix up this chart to include it. So that is everything but water vapor in the atmosphere. But now let's look at water vapor, because the presence of water vapor in the atmosphere is extremely important to how climate works. That the changes in the amount of water vapor held by a body of air are a big driver of climate processes. So when we talk about the amount of water vapor in the air, we describe that as humidity. So humidity is the amount of water vapor that's in a given blob of air. And we can describe that humidity in two different ways. So one way we can describe it is the absolute humidity. So that is the mass of water in a given mass of air. So we often describe that in grams per kilogram. So we've got a certain amount of, let's say, a kilogram of dry air, so everything but the water vapor. How many grams of water vapor are in there along with that kilogram of everything else? But that's absolute humidity. That's just the mass of water that is in that air. But you're probably more familiar with descriptions of relative humidity. So relative humidity is a percentage, and it's the percentage of the air's capacity to hold moisture that is currently taken up. So there is a ceiling, a limit on how much water vapor can be in a given amount of air. And so we can compare that maximum possible amount of water vapor that that air could hold to the amount of water vapor that's actually in the air. And we can express that as a percentage, and that percentage is our relative humidity. So another way to think of it is that you can think of relative humidity as being kind of how full the air is. The air has a certain amount of water vapor it could hold, and so the relative humidity is what percentage of that is filled up. So the picture there gives you kind of a conceptual diagram of what we're talking about here. So if we imagine rather than water vapor in air, we're imagining water in a cup. So if you have a 6-ounce glass and you put 6 ounces of water in it, then that glass's capacity is 100% filled, right? That glass can hold 6 ounces. It's got 6 ounces in it. It's 100% filled. So that's equivalent to 100% relative humidity. Then if you have a 9-ounce glass and you put that same amount of water in it, so 6 ounces of water into that glass, then that glass is now at 67% full, right? It's 2/3 full because it could hold up to 9 ounces, but it's only got 6 ounces in it. So those two glasses have the same absolute amount of water in them, right? They both contain 6 ounces of water, but one of them has a lower relative amount of water because its ability to hold water is greater. It could hold more than that 6 ounces, so it's only 67% full. And then you see if you get a 12-ounce glass and put 6 ounces of water in it, now you're at 50% full. Same 6 ounces of water, but the size of the glass has increased, and so it's now only 50% full with those 6 ounces. But then if you put more water into your 12-ounce glass, so now it has 9 ounces of water in it, it's now 75% full. So now we've increased the absolute amount of water in the glass and that has increased that relative humidity. So you can increase the relative humidity either by adding more water, increasing the absolute humidity, or by decreasing the size of your glass, decreasing the capacity of that air to hold moisture. And then likewise, you could decrease your relative humidity by either increasing the size of the glass, so there's more empty space, or by decreasing the absolute humidity, taking some of that water out. The key thing to note here, though, is that you can change the relative humidity without changing the absolute humidity. So without adding or removing water from the air, you can change the relative humidity by changing how much water that air is capable of holding. And the way that you do that, the way that you can change the amount of water, that total cap on the total amount of water that air could hold, is by changing its temperature. So a very key thing to remember, a thing that's going to come back again and again, is that hot air can hold more moisture than cold air. So if you increase the temperature of air, you increase its capacity to hold moisture, and at the same time, you decrease its relative humidity if no moisture is being added or subtracted. So if you keep your absolute humidity the same amount, same number of grams of water in that air, if you heat up the air, you increase its capacity to hold moisture, it's equivalent to making the glass bigger, and so your relative humidity goes down. And then the opposite is true if you cool that air. So if you cool off a mass of air without changing the absolute humidity, without changing the number of grams of water in it, you cool that air, you decrease the air's capacity to hold moisture. So it's like you're shrinking the glass, and so your relative humidity goes up. That same amount of water is now a larger percentage of the size that that air could potentially hold. Okay, it's a very important process there. Heating air decreases relative humidity. Cooling air increases relative humidity. Now, you may wonder what happens if our relative humidity goes above 100%. Right? What if we took that 6 ounces of water and poured it into a 3-ounce glass? Well, if you did that, your glass would hold on to 3 ounces of that water, and the other 3 ounces would spill out. Right? If you tried to pour the 6 ounces into a 3-ounce glass, the excess would spill out. So your glass would remain 100% full, but you'd lose a bunch of your water. You'd now be at a lower absolute humidity because you couldn't hang on to that water. You didn't have the capacity to absorb it. And so when that happens with air, that extra water is forced out as condensation. It becomes liquid. So it goes from water vapor to a liquid. So if you cool a mass of air, its capacity to hold moisture is going to shrink and shrink and shrink. When the air's maximum capacity is equal to the amount of moisture that's actually in it, you're at 100% relative humidity. If you continue to cool that air, continue to shrink the size of what that air can hold, then that excess water vapor that the air can no longer hold on to is going to condense into liquid. And so you can see that in a lot of different scenarios. So if you have the air up in the sky when this is happening, you get clouds. So the clouds are tiny little droplets of liquid water that have condensed out of air that can no longer hold all that water vapor. If it happens near the surface, you get things like dew. So when there's dew on the grass in the morning, that's because the air close to the Earth's surface cooled down below where it hit 100% humidity during the night, and so that excess moisture, that excess humidity that couldn't be held in the air anymore, condensed out as liquid that is then left on your grass. If you have a cold beverage and you get water droplets forming on the outside of your glass, that's because that cold drink is cooling off the air immediately around the glass, cooling it below where it would be at 100% relative humidity, and so that excess moisture is turning into condensation and getting stuck to your glass. So we had our sort of toy example there with glasses of water. Here's what this looks like with actual air. So this is at kind of typical air pressures. we have a relationship between the temperature of the air, the humidity, the amount of water in that air, and the relative humidity, what percentage of that air is filled. So this is a complicated graph to read, and luckily you're going to have some questions about this in your activity, but this comes from an interactive version of this graph. So you can just click on it and get your answers. So you don't have to squint at it and try to read it in detail, but I want to kind of walk you through it so you understand what this graph is doing. So let's say our air is at 25 degrees Celsius. So we read that along the bottom there, that is our temperature in degrees Celsius. So we have 25, and we go up the graph at that 25. And let's say that the air that we're interested in knowing about has 8 grams of water per kilogram of dry air. So for every kilogram of everything besides water that's in that air, it's got 8 grams of water vapor in it. If that's the case, we land at that point that is marked on the graph, the little marker there where the 25 degrees and 8 grams per kilogram come together. And then we can see that that is along the curved line that's labeled 40%. So under those conditions, 25 degrees with 8 grams per kilogram water vapor in the air, that is 40% relative humidity. And we can double check that if we were to continue upward at that 25 degrees, because you'll see that this graph, doesn't fill the complete rectangle. It has that curved edge on it because you can't go above 100% relative humidity. So that curved edge of the graph where everything stops is the 100% humidity line. So if we follow our 25 degrees up to that line, we'll see that that happens when our air has 20 grams per kilogram of water in it. So our maximum amount of water that 25 degree air can hold is 20 grams per kilogram. And of course, 8 is 40% of 20. Right? 8 is 40% of 20. So our air is holding currently 40% of the total amount of moisture that it could possibly hold. So if we were to cool off that air, so go back to our point and let's read it the other direction, right? So we're going to keep the amount of moisture in the air the same. We've got that 8 grams. And let's follow it over to the left as we're cooling down this air, right? As we get to about 18 degrees, we hit the 60% relative humidity line. And we continue on over, and eventually you can see just before 10, so like at about 11 degrees, we hit that 100% relative humidity edge of the graph, right? You can see that the dotted line for 8 grams per kilogram doesn't quite get over far enough to meet the dotted line for 10, so that's at about 11 degrees Celsius. At that point, our 8 grams per kilogram of moisture that are in the air are equal to that air's total capacity to hold moisture. The air can only hold 8 grams per kilogram, and so that would be 100% humidity. So we can raise the humidity all the way up to 100%, not by adding any moisture to the air, but simply by taking the air that we've got and cooling it down. And this chart shows that we'd have to cool our air with 8 grams per kilogram of moisture in it down to about 11 degrees Celsius before it hit 100% humidity. And if we were to continue to try to cool that air down, we would end up riding along that curved edge of the diagram. So we can't go above 100% humidity, so that would force some of our moisture out as condensation. So if we were to continue cooling our air, let's say we cooled it all the way down to 0 degrees. Well, we can't have 8 grams per kilogram of moisture in that air because that would be over 100% humidity. So instead, we'd end up at 0 degrees. You'd see that 100% humidity is about 4 grams per kilogram. So we'd still have 4 grams per kilogram of moisture in that air that we've cooled down to 0. But the other 4 grams, we started at 8, we're now at only 4 that can still be held onto by that air. The other 8 grams have now condensed out. They have formed a cloud, they have formed dew, they have formed some sort of liquid condensation. And then if we were to heat that air back up, right? So now we've squeezed out half that water and we heat the air back up, it's not necessarily going to reabsorb that water. Maybe that water has now been, blown away. It's been wiped off the glass, whatever. So we still just have that 4 grams per kilogram in the air. And if we heat it back up to 25 degrees, we can see that now we are at about 20% relative humidity. And that, again, makes sense, right? Air at 25, we said, can hold up to 20 grams per kilogram of moisture. And so if we have 4 in it, 4 is 20% of 20. So our air would be at 20% relative humidity when we heated it back up to 25, if we had taken it down to 0 and then back up. Okay, so key idea here, if you heat up air, you decrease its relative humidity, you cool air down, you increase its relative humidity, and once you increase that relative humidity past 100%, you can't go over 100%, so you stay at 100%, but the excess moisture now leaves the air because it becomes liquid condensation. So humidity itself can become a hazard to people. So your body is cooled by evaporative cooling when you're in hot conditions. So when you have water that is evaporating, that phase change from liquid to gas sucks up energy from the materials around it. So evaporation of water takes up energy, and that creates a cooling effect. So things will cool down if there's water on them that starts to evaporate. And so your body makes use of that principle when you sweat. So when you sweat, what your body is doing is it's putting a bunch of water on the outside of you, which then evaporates, and it pulls some energy, some thermal energy away from you as that evaporation happens, and cools you down. Right? So that's the basic idea behind sweating. Basic idea between like a dog panting, same thing. They're trying to get some water to evaporate and create a cooling effect. So your body is cooled by evaporative cooling when you are in a hot conditions and you start to sweat. So that's pretty important for maintaining your health. You have to maintain a constant internal body temperature, and sweating is one of your main ways to do that if the air around you is hot. But because evaporative cooling depends on water being able to evaporate, it's more effective at lower humidity. If the air has very little water vapor in it already, it's very easy for more to evaporate off of you and to cool you down as it does. If the air already is very humid, that already is mostly full in terms of the amount of water that it can hold, then it's going to be much harder to evaporate additional water into that air, and so it's going to be harder for you to cool off. And so you may have experienced that when you notice that on humid days, you get sweatier, right? Because you're sweating and that sweat is not evaporating quickly. And because of that, more humid air is going to feel hotter. So it may be the same temperature, but it's going to feel hotter because you're not experiencing that evaporative cooling effect. You're not getting that cooling down of your own body by evaporation of your sweat if the air is very humid, and so that sweat is slow to evaporate. And we often talk about this in terms of what we call the wet bulb temperature. So your standard temperatures are done with a dry thermometer. So you just have the thermometer in your air and it records the temperature of the air. If you were to get a little piece of cloth or cotton or something, get it wet, wrap it around the bulb of the thermometer, then that thermometer will now experience evaporative cooling. So that water from that wet cloth will start to evaporate and it will cool your thermometer. And so you can compare the temperature on a dry bulb thermometer, the thermometer that's just measuring the temperature in the air, and the temperature on a wet bulb thermometer that is measuring how much cooler it has gotten through evaporative cooling. So that evaporative cooling will cool down the dry bulb or the wet bulb thermometer as the water evaporates. So your wet bulb temperature is going to be usually lower than your dry bulb temperature because it is evaporatively cooled. But the difference will become less and less as the air gets more humid because less and less water is evaporating off of that wet bulb. And if you're at 100% relative humidity, that means no water can evaporate. The air is already full. It cannot accept any more water vapor. And so at 100% relative humidity, your dry bulb and wet bulb temperatures will be the same. So your wet bulb is essentially telling you how much cooler can you get through evaporative cooling. So for a person, that's how much cooler can you get by sweating or by splashing water on yourself to create evaporative cooling. Humans cannot survive extended periods of time, so we're talking, several hours to a day, at wet bulb temperatures above about 35 degrees Celsius, which is about 95 Fahrenheit. So if you are in a situation where the wet bulb temperature is above 35 Celsius for an extended period of time, you're going to start to suffer significant health impacts. And so this is a big concern for people who don't have access to other ways of getting cool and are experiencing very hot weather. So if you go into an air-conditioned building, then the air conditioning cools things off and you don't have to worry about evaporative cooling. But if you don't have access to air conditioning, so if either you are poor and so you can't afford air conditioning, or maybe you work outside, right? I've got this picture of some farm workers here. Farm workers have to be out in the field picking and weeding and everything else that they do. They can't be air conditioned while they're out there. So if the wet bulb temperature is above 35 Celsius for an extended period of time, for like a whole workday of these guys out picking, this looks like kale in this picture, they can suffer some serious health impacts because now their body isn't able to cool itself sufficiently to be able to maintain your health. So high humidity combined with high temperatures can be a serious health hazard for people. Okay, so let's now talk about the idea of weather versus climate. Both of these are ways of describing the conditions of the atmosphere, what is currently going on in the atmosphere. Weather describes the short-term conditions of the atmosphere. So a snapshot in time, we're looking at weather. So I've got a screenshot there of the weather report on the day that I'm recording this for Slippery Rock. And you can see that at the time I took this screenshot, it was 65 degrees out, 62% relative humidity, 30% or 30 inches air pressure, which is something that we won't get a chance to talk about in this class. Wind at 6 miles per hour. So we have all these numbers describing the conditions of the atmosphere in Slippery Rock at exactly the time that I took that screenshot off of weather.com. So even just in the time between when I took that screenshot and when I started doing this recording, right, just between preparing the PowerPoint and recording the lecture, that has probably changed. It's getting later in the day, so it's probably cooler. That probably also means the relative humidity has gone up if the air has cooled off and there hasn't been anything adding or subtracting water vapor to the atmosphere, then the relative humidity has probably gone up since then. Wind might have changed in strength, gotten faster or slower. So the weather is the short-term conditions. It is a snapshot in time, what's happening right now or at one specific point in time in the atmosphere. Climate is the long-term average conditions of the atmosphere. And conventionally, we talk about a 30-year time frame. So if we take 30 years of weather and average it together, that gives us our climate. So weather is short-term, climate is long-term average conditions. So our climate in Slippery Rock, we would describe as, well, what's the average temperature at this time of year? And 65 is, for early October, within the usual range. Right, so this day that I'm using as my example here happens to fall pretty well within that average. And we could then say that, well, what's going to be happening on October 12th, 2026? Well, we don't know what the exact temperature is going to be. We can't forecast the weather that far out, but climate tells us a pretty good guess that it's going to be in, the 60s. So we know that that's sort of the average temperature that we would get on a day at this point in the year. So climate is our long-term average conditions. So what we expect to happen in over a long period of time. So we can describe the climate and represent the climate of a place through something called a climograph. So a climograph is a combination of a bar graph of precipitation and a line graph of temperature. These are the two most important components of climate. So when we're describing the climate of a place, we are primarily describing the typical temperatures and precipitation that we get in that place over the course of a year. So what is the yearly pattern of temperature and precipitation in that place? So we can start by looking at the climograph I have there for Boston. Boston is in northeast United States, climate fairly similar to what we have in Slippery Rock. And so what you can see is if we first look at the temperatures, we get this yearly cycle of temperatures, right? That our temperatures are a little below freezing in January and February. This is average temperatures, quite cold there. They go up above 20 degrees Celsius in the middle of the summer and then come back down in the winter, right? And so if you've lived in Slippery Rock, you know what that's like, that this, shift back and forth between hot summer and cold winter. It's shown on the climograph there. Then if we look at the precipitation, you can see that you get close to 10 centimeters of precipitation basically every month. So the amount of precipitation falling in one month to the next in Boston tends to be fairly even. Again, average over the long term, obviously you'll get some wet months, some dry months, but when you average it all together, there's no month during the year in Boston that tends to get significantly more or significantly less precipitation than any other. And again, that's pretty similar to Slippery Rock. So in Slippery Rock, we don't really have certain months that are super rainy and others that are usually super dry. We tend to have, similar amounts of precipitation throughout the year. So that climograph describes that climate in Boston and is similar to what we're familiar with from Slippery Rock. If you look at the second one, Calcutta, India. If we look at the temperatures, you can see two key differences between the temperatures in Calcutta versus in Boston. Number one, the temperatures are overall higher. So Calcutta is closer to the equator. Right? You see Boston is 42.5 degrees north. Calcutta is only 22.5 degrees north, so it's much closer to the equator. So overall temperature is warmer throughout the year, and you can see that temperature has less variation over the course of the year. So the temperature range in Boston, and we're just talking average daily temperatures here, right? We're not even getting into the fact that the average daily temperature averages out, daytime high and nighttime low. But the average daily temperatures in Boston range over about, 15-ish degrees Celsius between the coldest months and the warmest months. In Calcutta, they range about 10 degrees between the warmest and coldest months. Right? So, about 25 degrees range in Boston to about 10 degrees range in Calcutta. So it's both hotter overall and less seasonal variation in temperature. On the other hand, Calcutta has a very big seasonal variation in precipitation. So you can see they have a very clear rainy season during the summer, and then it's very dry during the winter. So their seasons are, the change of the seasons there is more about changes in precipitation. They get tons of rain, way more rain than Boston ever gets during the summer, but then it gets extremely dry during the winter, much drier than Boston ever gets. So they get this big precipitation difference, even though the average, like if you were to average the entire year out, they wouldn't be that different. But in Calcutta, there's a big seasonal variation between summer and winter in precipitation. And then the last one I've got there is Christchurch, New Zealand. And so you can see Christchurch, New Zealand is at about the same latitude south as Boston is north, right? It's 43.5 south, so just 1 degree farther from the equator than Boston is. And you can see that temperature-wise, it shows a similar pattern to Boston, except reversed in that it is warm in January and cold in July because we're in the southern hemisphere. So the seasons happen at opposite times of the year. Right? So their summer is in December, January, February, and then it cools down in the middle of the year. That's when their winter is. You can see they likewise have fairly steady precipitation throughout the year, a little drier than Boston, but overall similar sort of pattern. So these are the kind of things that you can see from a climograph when you look at how temperature and precipitation typically go across the course of a year. Because again, these graphs are not representing any one year. These are averages over the course of 30 years. You take 30 years of data, average it all together. What's the average temperature in January, February, etc. And that gives you what you see on the graphs there. So we want to be able to explain some of these patterns. Why do we get different climates in different parts of the world? And so what I've got up here is just as an illustration, the conditions in January and July for temperature on the left, precipitation on the right. So we can look at these maps and start to think about the things that we might need to explain. Right? What do we need to explain? Why are some areas colder than others, other areas warmer? Why are some areas very rainy, other areas very dry? So if you want to pause this video for a second, take a look at what you see on these maps and try to generate a couple hypotheses. What are some things that you notice about the temperature and precipitation patterns? Maybe do one for each, right? One thing you notice about temperature patterns, one thing you notice about precipitation patterns from these maps, and then what do you think might be causing that? So I encourage you to pause the video and jot down some hypotheses, and then as I go through the next few slides, you can see if your hypotheses were on the right track, and we'll come back to these maps at the end, take a look at what's going on, and see how it matches up with the principles that we're going to learn. All right, so the first factor influencing climate that I want to talk about is latitude. So how close are you to the equators versus being close to the poles? So a key issue here is that the sun is so much bigger than the Earth that the sun's rays are striking the Earth more or less in parallel. So the sun is just so big that its rays are coming in basically parallel to the Earth. But the Earth is curved. So some parts of the Earth are going to get those solar rays coming down, kind of straight down vertically on them. Other places are going to get the sun's rays coming in at a low angle. The sun's going to be low in the sky as those rays come in. Because of that, some areas are going to get a lot more solar energy, because if you imagine a sun ray of a certain size, or a certain width, hits the ground, if it comes down perpendicular, you're concentrating that whole sun ray in a very small area. If that sun ray comes in at an angle, it's going to spread out over much more of the Earth's surface. So you can see on the diagram there how when those rays are coming in at an angle to the Earth's surface, so the Earth's surface is tilted away from where the sun is, then that solar ray is getting spread out over more area. So it's more diffuse, so you're getting less energy per square kilometer. So you're getting less warming happening. So whatever point on the Earth is directly beneath the sun, where the solar rays are coming in perpendicular to the surface, is going to get more energy, and so it's going to be warmer. And so the picture here is showing the Earth kind of straight up vertical. So that most concentrated energy is hitting right at the equator. That is true at 2 points during the year, but during the rest of the year, the Earth is going to be tilted more or less in one direction or another. So the Earth is tilted at about 23.5 degrees from vertical. So that means that the point that is getting that very direct sunlight is going to shift. It's not going to be exactly at the equator. It's going to wander northward to 23.5 degrees north, and then back down to 23.5 degrees south, and then back up. So over the course of the year, that subsolar point, the point where the sun is directly overhead, is going to shift back and forth, northward and southward, because the Earth is tilted. And so sometimes one hemisphere is tilted towards the sun, and so it's getting more direct sun rays. During the other half of the year, the other hemisphere is tilted towards the sun and is getting the more direct sun rays. And so if we go back to our map here, you can see that the hottest area in January is a little to the south of the equator, whereas in July, the hottest area is a little to the north of the equator. So in January, the southern hemisphere is tilted a little towards the sun. So the spot that's getting that direct overhead rays from the sun is to the south of the equator. In July, the Earth is the northern hemisphere is tilted a little bit towards the sun, so the point that's getting that most direct sunlight is a little bit to the north of the equator. So latitude is our first big factor affecting climate. It's going to be warmer closer to the equator, and it's specifically going to be warmest when your hemisphere is tilted towards the sun, so that the spot that the sunlight is hitting most directly is to your side of the equator. Another important factor affecting climate is altitude. So within the troposphere, and this is one of the things that defines the troposphere, so it's not true of the other layers, but within the troposphere, temperature decreases at higher altitudes. So the higher up you get from the center of the Earth, the colder it's going to get. And so you've probably experienced that. We have big enough mountains around western Pennsylvania that you've probably experienced, where if you are down in a valley and then you go up to the top of a mountain, you can notice that it has gotten colder up there. You've probably seen days where it was cold enough on top of the mountains for snow to stick, but by the time that snow fell down into the valleys, it was melting. And the snow up in the mountains will stay around longer. It will take longer to melt on a warm day than the snow down in the valleys. And that's just with the relatively small mountains that we have here in Pennsylvania. We get even more extreme altitude differences in temperature when we go to very high mountains. And so a classic illustration of this is the altitudinal zonation in the Andes Mountains. So the Andes Mountains along the west coast of South America are some of the tallest mountains in the world, second only to the Himalayas. And so you get a lot of altitude change over a very short distance. So you can very quickly move between these altitudinal zones and experience the difference in temperatures. And these differences in temperatures have led to differences in the way of life of people living at different heights on the mountain. So if you are in a place like Ecuador or Peru that has these very tall mountains, you get different products being grown at different levels of the mountains because of the climate difference. So at the very bottom of the mountains, close to sea level, you get what's known in Spanish as the tierra caliente, the hot land. And you can see on the diagram there that in that zone you can grow tropical crops like rice, sugarcane, cacao, rubber, bananas. Right? Those are all crops that need very hot conditions. You can grow them near the bottom of the mountain. Once you get up above about 1,000 meters in height, you enter the tierra templada, which means the temperate land. And so at that zone, you're growing temperate zone crops. So these are things like maize, sugarcane, also grows there, wheat, coffee, cotton. So these are crops that need a more moderate climate. You can grow them by going up the mountain. Continue going up the mountain above about 2,000 meters, you hit the tierra fria, the cold land. And there you can grow cold weather crops like potatoes and barley. So, you know, your rubber won't grow that high up the mountains, but your potatoes will. And then if you continue going up to the very tops of the mountains, you get to the tierra helada, which is the icy land. And so up there, it's so cold that you can't grow any plants, crops anymore, but you can raise animals like llamas that have thick coats of fur. So you get all these different zones with all these different kinds of crops in a very short horizontal distance because altitude changes the temperature so much. So the higher you go, the cooler it gets. Another important factor shaping climate is ocean currents. So within an ocean basin, your water is moving, right? We're getting convection happening. So water near the equator that's getting warmed up, right? Remembering our latitude factor there, right? Water near the equator is getting warmed up, and then it's going to flow towards the poles, and then the water near the poles is cooling off, and it's going to flow down towards the equator. So we're going to get this circulation. Warm water from the equators flowing towards the poles, cold water from the poles flowing back to the equator. So it's going to, the water's kind of going to move in a cycle. It's going to go to the equator, get warmed up, flow back to the poles, cool down, flow back to the equator, get warmed up, go to the poles, and cool down. So we're going to make this little circle in each ocean basin. We call that circle a gyre. So we have a gyre in each major ocean basin. You can see 5 of them there, right? We've got North Atlantic, South Atlantic, North Pacific, South Pacific, and then we've got the Indian Ocean. There's no North Indian Ocean, one, because the Indian Ocean is nearly all in the southern hemisphere. And the equator is kind of a dividing line right there, because that's where the water gets warmest. So we've got these gyres forming, and so they're going to create ocean currents. They're going to run up one coast, the coast of a continent on one side of the ocean, and down the coast of the continents on the other side of the ocean. And you'll notice from looking at this map that the warm currents with the reddish arrows we find on the east coasts of all of our continents in both hemispheres, and we find a cold current with the dark blue arrow on the west coast of each continent. So we have this very consistent pattern. Cold currents on the west coast, and that's going to cool down the climate along that part of the continent, and warm currents on the east coasts. So these gyres are making this consistent pattern. And the reason for this is something known as the Coriolis effect. Coriolis effect is a result of the Earth's rotation. So the Earth is a sphere and it is rotating. So what that means is everything on the Earth goes once around in one day. But if you're at the equator, that means you're going a lot farther in one day than someone close to the poles. So the pole, you're making this little circle over the course of the day. Near the equator, you're making a giant circle over the course of the day. So things at the equator are moving a lot faster than things near the poles. You've got a lot more distance to cover in that one day. When a body of water or air starts to move across the surface of the Earth, it's going to have a rotational speed based on where it started from. But the place that it's going to is going to be rotating at a different speed. So if you are at the equator, you're rotating very, very fast, and then you move towards one of the poles, the area you're moving towards is not rotating as fast. So you're going to start to get ahead of the Earth's surface because you're still spinning as fast as the equator. And so you are getting ahead of the Earth's surface below you that's now spinning more slowly because we're closer to the poles, making a smaller circle. On the other hand, if you start out near the poles, you're spinning more slowly, you start to move towards the equator, the Earth is basically getting ahead of you. So you're lagging behind where the surface of the Earth is because you're not spinning as fast because you're picking up your speed from the place that you left from. So the difference in rotational speeds between your origin point and your destination point are going to create a seeming deflection. So from the point of view of somebody standing on the surface of the Earth, it's going to seem like bodies of air and water moving over long distances are being deflected to one side. They're not actually being deflected, it's just that they are rotating faster or slower than you are, and so they seem to get ahead of you or fall behind you. So this apparent deflection from the point of view of a person standing on the Earth is going to go to the right in the northern hemisphere, to the left in the southern hemisphere. So you're going to get deflection to the right, resulting in a clockwise movement in the northern hemisphere. You get deflection to the left, creating counterclockwise movement in the southern hemisphere. And you can see that with these gyres, right? You can see the gyres in the northern hemisphere are circulating clockwise. The ones in the southern hemisphere are circulating counterclockwise. You can imagine if that water was trying to move straight in the northern hemisphere, it keeps veering to the right and eventually curves around clockwise. Southern hemisphere, if that water tries to move straight, veers to the left, it's going to end up curving around counterclockwise. So the Coriolis effect is something that I think is much, much easier to understand if you can see an animation of it. Because, if you're having trouble visualizing what I'm talking about with, this apparent deflection because of differing rotational speeds. So one of the links on D2L is to a YouTube video that shows, animated how the Coriolis effect works. I think that'll probably be much more clear to you than me trying to just explain it in words. But the key thing to remember, even if you don't quite grasp how it all works, the key thing to remember is that the Coriolis effect makes things veer to the right in the northern hemisphere, to the left in the southern hemisphere, and so that creates a clockwise rotation in the northern hemisphere, a counterclockwise rotation in the southern hemisphere. All right, another important factor shaping climate is something called the primary circulation. And so this is a very complicated model that I'm not going to go through all of the details of, because this is one slide in one PowerPoint lesson. But I'm going to try to pick out the key takeaways from the primary circulation. So the primary circulation is the way that air moves around the Earth. And because of the combination of the Earth's rotation and the uneven heating that we get from the sun, because the sun is giving us concentrated energy at the place where the sun's directly overhead, and much more diffuse energy out to the polar directions from there, we get this pattern of rising and sinking air. So air will flow along the Earth's surface to a certain place. It will rise up into the upper atmosphere, flow back to where it came from, and sink back down. And this is all happening within the troposphere. So when we talk about upper atmosphere, we're really talking about top of the troposphere. Right? So the air will go across the surface, go rise up, flow back through the upper part of the troposphere, and then sink back down to the surface. And so we get these three cells, these three bands of rising and sinking air that create these zones of where air is primarily rising or primarily sinking based on how far they are from the spot that's getting the most direct sunlight. So this is all centered on that subsolar point, the point that's getting the most direct concentrated solar energy. So any place that we have rising air, as our air rises, it's going to cool, right? Remember back to our discussion of altitude? The higher up you go in the troposphere, the colder it gets. So our air is going to cool off as it rises. And as it cools, that's going to increase the relative humidity, right? Because the air can't hold as much moisture, so that maximum is going to decrease. So how full that air is going to increase. That percentage is going to go up. Eventually, that air is going to cool off enough that it can't hold all of its moisture anymore. Its maximum amount that it can hold is now less than the moisture that's there, so that excess is going to condense out. And that condensation is eventually going to fall as precipitation. So rising air leads to cooling, leads to increased relative humidity, leads to condensation and precipitation. Okay, so rising, cooling, increased relative humidity, precipitation. And so we have two main places on Earth where we're going to see that phenomenon happen. Two main spots where the air is rising. That is around the equator, 0 degrees, and at about 60 degrees north and south. So these are going to shift northward and southward because of the tilt of the Earth. So over the course of the year, these are going to slide north and south by some distance, but somewhere close-ish to the equator, and then somewhere around 60 north and 60 south, we get rising air. Then we get the opposite happening in between there. So at about 30 north and 30 south, and then again at the poles, 90 north and 90 south, we get the air sinking. So it rose at 0 and 60, and it's got to come back down, so it's going to come back down at 30 and 90. And so when air sinks, it's going to warm up, right? Higher in the troposphere is colder, lower is warmer, so the air is going to warm up as it sinks down. As it warms, the relative humidity is going to decrease because the air's capacity to hold moisture is going to grow, but there's nothing adding more moisture to it, so the moisture that it's got becomes a smaller and smaller percentage as the total capacity grows. So our relative humidity is decreasing, and so because of that, there's nothing to force condensation to happen. All right, our air can easily hold all that water vapor. There's nothing squeezing it out into liquid form where it can fall as precipitation. So we're going to get a dry climate at places where we have sinking air. So at about 30 north and south and about 90 north and south, which is the poles, we have that sinking air, and we are going to get a dry climate. So those are the key things for you to remember from the primary circulation, are that where we have rising air, we get precipitation, and that's happening roughly around 0 degrees and 60 north and south. Where we have sinking air, we're going to have dry conditions at about 30 north and south and 90 north and south. Okay, another important climate factor is what's called the rain shadow effect. So in some ways, this works very similar to the primary circulation. It's just a different mechanism for air to be pushed up and down. So rather than this primary circulation causing air to rise or sink, we have topography. So when we have a big mountain and our air is trying to go across that mountain, then it's going to be forced upward and then it's going to come back downward. And just like with the primary circulation, when the air goes upward, it's going to cool off. As it cools off, the relative humidity is going to increase because the air's capacity to hold moisture is going to shrink. Eventually, it's going to shrink so much that we pass 100% relative humidity. The extra moisture comes out as condensation, and it falls as precipitation. So where the air is rising up the mountain, we are going to get precipitation because it's cooling off, and that cooling is squeezing that extra moisture out of the air. And we call that the windward side of the mountain. And so the side of the mountain that the air hits first is the windward side, and it's going to get lots of precipitation. Now the air is eventually going to get over the top of the mountain and come down the other side. So the air is now sinking. It's going down, so it's going to warm up. As it warms up, its capacity to hold moisture is going to increase, and so its relative humidity is going to decrease. The moisture that's in it is a smaller and smaller percentage of its total capacity. And so there's nothing to cause condensation because the air can easily hold all that water vapor, and so you're going to get a dry climate. So that side where the air is coming back down the mountain, we call the leeward side. So windward side, the air is going up. You can think of it as that's the side the wind hits first. Windward side, air goes up, cools off, we get precipitation. Leeward side, the air comes down, warms up, and we get dry conditions. And that's what's sometimes called the rain shadow. So it's like the mountains are casting this shadow where you can't find any rain because the air is now coming down, warming up, nothing to cause condensation and precipitation. And I think South America provides a really nice example of the rain shadow effect. So if you look at the southern part of South America, and you look at roughly the border between Argentina and Chile. So if you can see my pointer right here, kind of along the west coast of the southern part of South America, we have the Andes Mountains. So they're very high. They're high enough to cause a significant rain shadow effect. And you can see that in the northern part of Chile, things are very dry. The lighter colors here mean less precipitation. It's very dry in northern Chile and comparatively wetter in northern Argentina. But then we go south of there, southern Chile, very wet, southern Argentina, comparatively quite dry. What we're seeing here is the rain shadow effect going in two different directions because of what direction the winds are trying to cross the Andes Mountains. So this is another part of the primary circulation that I didn't want to take the time to get into, so I'll just explain that closer to the equator, our prevailing winds are going from east to west. So they're going from east to west across the Andes. So as they go up the eastern slope of the Andes, we get precipitation as the air rises and cools. And then as it comes down the westward side of the Andes in northern Chile, it's warming up, and so it's going to be dry. There's nothing to squeeze out moisture as precipitation. But in the southern part of South America, the prevailing winds are going in the opposite direction. So the prevailing winds are now going from west to east in this part of South America. And so we get the same phenomenon. It's just swapped around because the wind is blowing in the opposite direction. So as the winds go up the westward side of the Andes in southern Chile, the air is cooling off. That's causing condensation, precipitation. So we get wet conditions in southern Chile. And then as the air comes down the eastern side of the Andes into southern Argentina, it's warming up. There's nothing to squeeze that moisture out as precipitation. And so we get very dry conditions in southern Argentina. So we get those rain shadows showing up there, opposite sides of the Andes, just because the winds are blowing in opposite directions. So we can come back to our maps here and we can see some of these effects. So I already flipped back to show you the effect of latitude, that we've got warmer temperatures closer to the equator, cooler temperatures nearer to the poles, and that the center of that, where the warmest temperatures are, shifts to the south in the southern hemisphere summer, which is northern hemisphere winter, in January, and then shifts north of the equator in the northern hemisphere summer, which is southern hemisphere winter, in July. Then we can see the effects of altitude. So if you look, it's particularly visible in the July map here. You can see some of our highest mountains, like the Himalayas in Asia. You can see them being significantly colder than the areas around them. You can also see the Andes, notably colder than the areas around them. You can see the Rockies in the western United States and Canada, significantly colder than the areas around them. So there we're seeing the effects of that altitude, that you're going up the mountains, and so it is getting colder. We can see the effect of ocean currents. So if you look at North America, for example, you see it's warmer on the East Coast than at the corresponding place on the West Coast. If you look kind of straight across the continent there, it's colder on the West Coast than at the same latitude on the East Coast. That's because we have a warm current flowing up the eastern side of North America, and we have a cold current flowing down the West Coast. Because in both cases, we have a clockwise gyre of ocean currents in the northern part of the ocean, the North Atlantic and the North Pacific. So that creates a warm current going up the east coast of the continent and a cold current coming down the west coast. We can see the effects of the primary circulation. So if we flip over to our precipitation maps, you can see that the spot where the sun is most directly overhead, so that's a little south of the equator in January, it's a little north of the equator in July, are some of the wettest parts of Earth. So the darker blues are the wetter areas on here. So we get a band of high precipitation across the middle of the Earth, kind of shifts a little to the south in January, a little to the north in July. That is that zone of rising air causing cooling, causing precipitation. And then you can see to either side of that, very dry conditions. So Africa makes it really visible here, sort of the easiest place for you to see it, but you can see it in other areas as well, where you've got these very dry conditions. That's where air is descending. And so you'll find that's roughly around 30 degrees north and south. It's shifted a little in one direction or the other, depending on the season, but we are getting the effects of that air that is sinking, warming up, and so there's nothing causing condensation and precipitation at those latitudes. We can also see the rain shadow effect. So you can see it in South America in the same way that I was illustrating it in the previous slide. You can also see it in North America. So you may be familiar in North America with how rainy it is on the West Coast in places like Seattle. That's because those are on the windward side of the mountains. So the air is blowing from west to east across most of the United States. And so that air is hitting the mountains along the west coast, going up, cooling off, dropping a lot of precipitation right along the west coast in places like Portland and Seattle. But then by the time the air gets across the mountains into the central part of the United States, it's now coming down, heating up, and so we get much less precipitation in the central part of the United States, to the east of the Rocky Mountains. So we can see all of those climate factors at work in our maps of global temperature and precipitation. So I'm going to leave it there for this lesson, and I will see you next week.